So like I said, this problem right here is not really like the sample one that I did, because the sample one that I did, it had charges in 3 different corners, and you had to figure the force on one of those charges based on the charges in the other 2 corners. This one is electric field. So it says a rectangle has sides of horizontal length 10. So I'll put that in here. So horizontal length 10 meters and vertical length 6 meters. And it says a positive charge of 13 microcoulombs is fixed to the bottom left corner. Now, I'm just going to put what the charge is, whether it's plus or minus. I will put in the value later on, but for now, I'm just going to put what's plus and what's minus, because that's all I need to determine the direction of the resultant, or whatever I'm trying to figure out here. So there's going to be a positive in this corner right there. And then it says, what charge must be fixed to the bottom right corner? So what charge do I have to put over here so that the electric field in the y direction at the upper right corner of the rectangle is 0? Now they're only asking to cancel out the y direction of the electric field. In order for me to cancel the x direction, I would also have to put a charge in that corner. Because if I'm trying to figure, if I want to cancel out the electric field in this corner, then I need, this one will cancel out the y because it would be along that line, and this one would cancel out the x. So I'm only asking you to cancel out the y component. I would need 2, like I said, I would need 2 charges to completely cancel out the electric field in that corner. So if you remember, electric field vectors go away from positive charges. So the direction of the electric field here is going to be in that direction. Okay, let me see if I have it right there. Okay, so that's my electric field in that corner, caused by this charge right there. So I can take that electric field, and I'll just label it E right now, and I can take that electric field and break it into its x and its y components. So its x component would be in that direction, and its y component would be in that direction. So I only want to cancel out the y. Well, I can cancel out the y by putting a charge in this corner that will cancel out that arrow right there. So I need the electric field, I need an electric field in this direction so that this one will cancel that one. All right, because if those 2 are canceled out, I will have canceled out the electric field in the y direction. And like I said, if I wanted to completely cancel out the electric field, I would also have to put a charge in this corner, and I would have the charge in this corner make an electric field go that way, so that this one would cancel that one. But we're only looking to cancel one direction. So but the next thing I need to do is, I know that if I draw a line from here to here, that the angle here is going to be the same as the angle there. And I need that angle in order to figure out how much that is, because that's the y component of my electric field. So I'm going to get that angle by using the inverse tangent, because I know the opposite side and I know the adjacent side. So if I know the lengths of these 2 sides, I can solve for that angle. And if I know that angle, I'll know the angle up there. So let's take care of that first. I mean, there's a few things we need to do. It doesn't really matter what order we solve them. So let's get the angle, because I know I'm going to need the angle. So the angle is going to equal the inverse tangent of the opposite over the adjacent, which is 6/10. That's the ratio of the opposite sides of the adjacent, or I could have written 3 over 5 or 0.6. And what do you get for that angle? 30.96, so that would be 31.0 degrees is the angle. Now another thing that I'm going to need is if I want to know what the electric field is in this corner caused by that charge, I need to know that distance. I need to know the distance from there to there. So I now have to use the Pythagorean theorem that a squared plus b squared equals c squared. So I want that length because that's how far away I am from that charge. So I'm going to need that number. That's going to be my r. So I'm going to have that my r is going to equal the square root of 6 meters squared plus 10 meters squared. So remember, a squared plus b squared equals c squared. C equals the square root of a squared and b squared. So there's the a and the b. And if you solve that, what do you get for the r? $11.7. All right, so we have that. Now, actually, now we'll get the electric field. So we're going to get this number. First, I'm going to get this, and then I'll get that, and then from that, I'll be able to figure out what charge. Well, one thing that I do know is I can figure out whether it's going to be positive or negative. What charge will be in this corner? Will it be a positive or a negative charge? It'll be a negative because, remember, electric field intensity, electric field vectors go away from positives and they go towards negatives. So there has to be a negative in that corner. So I know that this is going to be a negative in that corner. And that's ultimately what I'm looking for. What value? So the next thing is, let's get the electric field. Well, we have a formula. Electric field equals KQ over R squared. And we have all those numbers. So we can put them all in. K is 9 times 10 to the 9th Newton meters squared per Coulomb squared. So that's Coulomb's constant. And the Q is given in the problem as 13 microcoulombs. So I'm going to write that as 13 times 10 to the negative 6 coulombs. And I'm going to divide that by the distance between where that charge is and where I'm looking at the electric field. So that's why I needed that 11.7, because the electric field here is going to be greater than there. And it's going to be greater there than there. The further away you get, because look, the electric field varies with the distance from the charge squared. So if you double the distance away, you're going to get 1/4 of the electric field. If you triple the distance, you're going to get 1/9 of the electric field. So we're at that distance away. So we need to figure out what the electric field is right there. So I'm going to put in 11.7 meters. And what do you get when you solve this? You can see here there's a lot of little things I can give you credit for. If you don't solve the problem, if you get me the angle, well, I have to give you some points for that. You solve for the r, I give you points for that. So maybe 2 points, 2 points, another 2 points. I mean, the whole problem is only worth 10 points, so it's going to be hard to stretch out the points. You have an answer? 854.7, so we'll say 855 newtons per coulomb. Okay, it's going to be newtons per coulomb because the meter squared will cancel the meter squared. One of the coulombs will cancel. So I'll still have newtons per coulomb. So that's my E. Now, what I want is I want this because I'm only trying to cancel out the y direction. So I need to figure out what that is. So we know that the angle right here is 31 degrees. So we know the angle and we know the hypotenuse. So we're looking for the opposite side. So what trig function will I use? Sine. So I didn't give it like, I'm only calling it E. So now I'm just going to have E in the y direction. So I didn't call it E1 or E2. The only electric field on the picture is 1. It's the only thing I labeled, so I just called it E. So electric field in the y direction is going to be E times the sine of the angle. So we're going to take 855 newtons per coulomb, and we're going to multiply that by the sine of 31 degrees. So it's going to be about half of that number, 430 about, or somewhere around there. What is it? 440. So now that we know what the amount of the electric field is that we have to have, and we know how far away the charge is going to be to create that electric field, we can figure out the charge. So I'm now going to rearrange this equation to solve for the charge in that corner. I know what the electric field has to be, and I know how far away that charge is from the upper right corner. So rearranging this formula right here, and you're going to get Q equals E R squared over K. But the E here is EY, because that's the value. So that's, we're not going to be using this E up here. We're using that E because that's the amount of electric field we need to create from that charge in the bottom right corner. So, whoops, if I put those numbers in, I'm going to have 440 newtons per coulomb. The distance between where the upper right corner and the lower right corner is 6 meters. So 6 meters squared. And then we're dividing it by 9 times 10 to the 9th Newton meters squared per coulomb squared. So you can see the newtons cancel with the newtons, the meters squared cancels the meters squared, coulomb cancels with one of the coulombs, and I'm left with 1 coulomb in the denominator of the denominator. So my answer will be in coulombs if you solve this. And hopefully you get for that answer. Now I know it's going to be a negative, right? I know it's a negative because of the direction it has to be in. So the answer is should be negative 1.76 times 10 to the negative 6 coulombs.